Okay, hello everyone. So welcome to my winter special series, and this is chapter 1. So this winter special series is aimed at introducing quantum computing and some quantum devices or even cryogenic CMOS, both circuits, devices, and modeling, and all of this to beginners. So we are aiming at beginners, alright? And this is chapter 1, which is the first of the everything to come. I hope you guys can enjoy this video and we'll have a good time together. Okay, we start by quoting a famous person, Richard Feynman, all right? Okay, he said that nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical, and it is not an easy question. So the problem we are facing when doing research about quantum computing is that it's a very new and field, so nobody knows everything. So we are learning as we progresses. So do please point out my mistakes if you spot any, and we'll make progress together. So here's the references. So the top two references are from Elsevier. There are research articles on Elsevier, and the third article is IEDM paper published by Intel last year. And the fourth reference is published by Professor Lan Wei. She did a introduction to quantum computing section on ISCC forum last year. So we start by answering an important question. So what is qubit? Well, classical bits is either 0 or 1. We use classical bits in our computers, in our cell phones, and the classical bits 0 or 1 are implemented, for example, in DRAM is by the charges stored in the capacitors, and in CPUs of classical computers, 0 or 1s, the classical bits are represented by voltage high or low. However, in a quantum computer, the qubit system, the state of the qubit system is a superposition of 0 and 1, and the parameters before the 0 and 1 state, alpha and beta, sort of links to the probability of finding these two states. Okay, and for example, we are only talking about a one qubit system. So for a one qubit system, the states are either 0 or 1, so the summation of the square products of these two parameters must equals to 1. Okay? So as we scale the number of qubits up, the number of states available is increasing exponentially. Okay, so for example, when we have 2 qubits, then we have 4 states possible. In 3 qubits, we have 8 states possible. So as you can see, when we have n qubits, the number of states available is 2 to the power of n. So the whole general state, the overall state of the system is a superposition of 2 to the power of n vector states. And such a general state exists in a complex Hilbert space. So having acquired the knowledge of what is qubit and what is the qubit states, and we come to the manipulation of these states. Okay, and the quantum computer can be as simple as a single molecule or a single atom. The state is determined by the orientation of its spins, and these states can be manipulated by RF pulses. We'll come to the detail of such operation later. And in general, in order to form a logic quantum gate, such gates must be able to perform unitary transformations on the state, which means that the Hamiltonian matrix representing such transitions must be unitary. Now we will take a look at two examples of quantum logic gates. Uh, on the left, we have an example of single qubit gates, and on the right, we have two qubit gates. So on the left, we have a gate that is capable of basically turning a pure zero state into a equally superposition of 0 and 1 state. Okay, and this state, the C naught quantum gate, is capable of rotating the another qubit on condition of the state of the first qubit. And as the number of qubits grow linearly, the Hilbert space, the dimensions of Hilbert space would grow exponentially. So when we have an n qubit situation, the dimensions of the Hilbert space will be 2 to the power of n. And the coupling between these physical states, these physical qubits can be implemented by physical interactions between these qubits. So in this slide, we will talk about the requirements for a qubit to be good. Okay, many qubit system has been constructed. Okay, those atomic systems where qubits are atoms, and they can exhibit a very long coherence time, but it's difficult for them to link each other in an efficient way. However, when we come to the silicon spin qubits, the semiconductor quantum dots have been introduced. So many people are puzzling about the physical nature about semiconductor quantum dots. I think we can just simply think of it as a transparent sphere containing numerous electrons. Okay, so let me say that again, a transparent sphere containing numerous electrons is what we can think of what is equivalent of a quantum dot. Obviously, such a transparent sphere does not exist in reality. It is a sort of a field, a quantum well. The quantum well is formed by the potential landscape of the energy field. Okay, such quantum dots is not an actual atom, but we can regard it as an artificial atom. Yeah, so this gives us a way to combine atomic properties in semiconductors. Okay, semiconductor obviously we know is the fundamental of the whole uh, microelectronic industry. So far in the research field, single quantum dots has been used to form logic gates, and these quantum dots are embedded in solid-state materials such as silicon or basically pure silicon-28, or recently silicon germanium system. Uh, we can tune the tunnel coupling between these quantum dots via the gate potential in an electrical way, and also optically we can use light to tune the tunnel coupling as well. However, in such a material system, there's many well disturbances. The disturbances between the electrons and phonons. Phonons are just basically the thermal vibration of those lattices, and the impurities in the semiconductor material can lead to a very fast relaxation of those quantum states, and thus lead to a very short coherence time. Speaking of relaxation, okay, so we are going to take a look at what it is actually, the physical nature of it. Um, well, T1 is the relaxation time, which means the time it took by the qubit to decay from state 1 to state 0, and t phi is the dephasing time, okay, which is the time it takes the qubit to re-randomize the phase phi, and the coherence time T2 is given by this equation. It is related to T1 and T phi simultaneously. So in order to understand the modern technologies that we use to manipulate the qubit states, we must learn a few more physical features. The first one is the Zeeman splitting. Okay, so when we apply a strong external magnetic field, say in the positive z-axis direction, then the two qubit logical states 0 and 1 would have different energy levels, and the energy difference between these two spin states is what we call the Zeeman splitting. And we are going to learn some math that is relating to this topic, and the time evolution of spin 1/2 nucleus in the magnetic field B0 along z-axis is governed by this Hamiltonian operator. And in this operator, the parameter gamma is the geomagnetic ratio of the nucleus, and Iz, the matrix Iz, is the angular momentum of the nuclear spin in the z direction. And we define omega over 2 pi, where omega is gamma multiplied by B0 is the precession frequency, or the Lamour frequency that we hear so often. And the nuclear magnetic moment, the Ix, Iy, and Iz are related to the Pauli matrices. Okay, so we're going to do some math operations to see the energy difference in these two states. So when we do such an operation to the Hamiltonian operator H0, we obtain, after doing all these linear algebra operations, we obtain the energy level for the zero state, which is minus h reduced Planck's constant multiplied by omega 0 divided by 2. And the same operation can be done to obtain the energy level for the one state, which is this, the direct opposite of the energy level for zero state. And the energy difference between these two states is obtained as the reduced Planck's constant multiplied by the angular frequency. And finally, the Lamour frequency can be obtained by this equation. Okay, the Lamour frequency W by the W0, omega 0 is equals to delta E divided by the reduced Planck constant. So having acquired the knowledge of Lamour frequency, then we can take a look at the modern CNM scheme for the qubit state control. CNM is short for control and measurement. Okay, so these two pictures are posed by Intel, and what they do to manipulate the state of their qubits is they use AC current or voltage pulses, and such pulses is at the Lamour frequency of the qubit system. Okay, so in the first one, so in the first one, this one is called the ESR method, the electron spin resonance. And this line, the line in brown, is our ESR line. So what it does is basically it is conducting out AC current through such a circuit, and the AC current can generate an oscillating magnetic field at the qubit position, and in such way that we can use the oscillating magnetic field that is at the Lamour frequency of the qubit to manipulate the spin or the state of the qubit. So as we can see here, there's the Rabi oscillations of such a qubit displayed here. And if we change the time scale we can see that as we progresses with such oscillating operation, the spin-up probability will eventually decohere into a decoherent state. So the coherence time T2 can be measured as 3.7 milliseconds around that value. So this is the latest work published by Intel. And this is also another technique to manipulate the state of the qubit. Intel applied this method in their silicon and silicon germanium material system. So as we can see, there's a darker brown line here. That is actually a layer of silicon germanium, and the lighter brown is the pure silicon 28 material, and the yellow one is representing the qubit. So instead of applying oscillating magnetic field as we do when using the ESR line, what we do here is that we place a cobalt, a micro cobalt magnet on top of the qubit. And then what we do is that we apply AC voltages to the gates, and the gates would when applying different voltage, we would control the position of the qubit. So when we are applying AC gate voltages, and what we do basically is oscillating the position of the qubit up and down at the Larmor frequency. In this way, the qubit would see the static magnetic field as if it were a AC magnetic field. In this way, we can also manipulate the state of the qubit. And the decoherence time in such a material system is measured to be around 1.1 millisecond. And that's all for the presentation today, and I wish you all a very, very happy new year. We'll see you next time.